All right, so in this video, we're going to continue to look at chemical reactions, but now we're going to start to look at some of the math related to those. So we're going to be able to determine how much of a given reactant we're going to need to produce a certain amount of a product that we want. If we know how much of a reactant we have, we're going to be able to determine how much of another reactant do we need to fully react with it. And then as we go through it, we'll also see just different types of analysis related to chemical reactions. And with this, we're going to start by looking at stoichiometry. So with that, we're essentially just going to be looking at the relationship between these different species. So with the chemistry of species, it's just referring to any chemical substance. So it could be an atom, an ion, a molecule, whatever. But when we're looking at these substances in a chemical reaction, the way that we're going to relate them to one another is based on the coefficients we have in that balanced chemical excuse me, that balanced chemical reaction. And with these coefficients, what they're going to represent is moles, but we can use a slightly less abstract example to kind of think about what this is going to kind of look like. Excuse me. So if we look at a recipe and kind of think of that as a chemical reaction, we can think of the ingredients as the reactants, and then whatever we're making as the product. So in this case, we can think of the pancake as the product, and then the pancake mix, the milk, the egg, as the reactants. And if we look at the quote-unquote reaction at the bottom here, it's telling us for every 1 cup of pancake mix, we're going to need 3/4 of a cup of milk and 1 egg. And then if we have all of that, we can make 8 pancakes. So what we can do is use the coefficients. So in this case, the 1, the 3/4, the 1, or the 8. We can use those coefficients in order to relate these different substances. So for instance, if we want to figure out how many eggs are we going to need to make 8 pancakes, what we can do is use those coefficients and then just go through a dimensional analysis type of process. And what this is telling us is we want to make 24 pancakes, but for every 8 pancakes, we need 1 egg. So we're going to need 3 eggs total. And if you'll notice, the numbers we're plugging in here are just the coefficients from the reaction, even though it's not, I guess it is actually a reaction, but we would never write this as a reaction, really. But the coefficients are just going with those same substances. So for every 8 pancakes, we needed 1 egg. And that's what we have in the parentheses here. So this is going to be exactly what we'll do with the chemical reactions, the chemical equations we're going to be dealing with. And when we do it, the important piece is that we have the balanced chemical reaction or chemical equation, because even if we go through the steps properly, if we don't have that balanced equation, or we don't have it balanced properly, we're automatically just going to wind up at the wrong spot. So we've got to always make sure we've got that balanced equation. That should be our first piece. And then the stoichiometry, the piece of it is just going to be based off of those coefficients. So if we look at the Haber process, so nitrogen and hydrogen combining to form ammonia, what this is telling us is, or it can be interpreted in a couple different ways. So we could think of it as 1 molecule of nitrogen plus 3 molecules of hydrogen are going to give us 2 molecules of ammonia. But if we remember that the mole is simply just a number, similar to a dozen, we could have 2 dozen nitrogen atoms, or excuse me, not 2 dozen, 1 dozen nitrogen molecules plus 3 dozen hydrogen molecules give us 2 dozen ammonia molecules. But again, mole is the same idea as dozen, just much, much larger, 6.022 times the 6.022 times 10 to the 23. So what we can do is think of this as moles. So 1 mole of 1 mole of nitrogen plus 3 moles of hydrogen give us 2 moles of ammonia. And when we think about these coefficients as moles, now we're going to be able to relate these substances to one another, whereas we can't do that with grams. So we can't go directly from one substance to another in terms of grams. We can only relate them based on moles. So if we think about these coefficients as mass, that's going to be incorrect, and we can see why pretty easily. But if these coefficients represented grams, we'd have 1 gram of nitrogen plus 3 grams of hydrogen, giving us 2 grams of ammonia. So we'd have 4 grams on the left, but we're only winding up with 2 on the right in that case. So we'd be losing half of the mass. We'd be violating the conservation of matter, which is just impossible. So with this one, again, coefficients represent moles, and then the moles are going to be the only way that we can relate one substance to another in a chemical reaction. We'll oftentimes have one step before that or one step after it, but we're always going to need the mole to mole step, as it's known, to relate something like, in this case, hydrogen to ammonia, nitrogen to ammonia, whatever it is, the process itself is actually always going to be the same. So we're going to be able to use this process to, for instance, if we wanted to produce a certain amount of ammonia, we could use that amount to figure out how much of either the reactants are we going to need. If we had a certain amount of hydrogen, we could figure out how much nitrogen are we going to need to react with all of that hydrogen. So we can relate any two substances in a chemical equation, and the process itself is going to be identical. It's just what is that information being used for is going to be different. And then, like I said, we may have one step at the beginning or one step at the end. But the mole to mole step is always going to be what we need in order to convert from one substance to another. So if we just look at a example where all we're doing is that mole to mole conversion, we've got the equation aluminum, 2 aluminum plus 3 iodine give us 2 moles of aluminum iodide. And we want to figure out how many moles of iodine are going to be required to react with 0.429 moles of aluminum. So the iodine is what we're looking for. We know the aluminum, and we've got the balanced chemical equation. So we've got all of the pieces we need in order to make this conversion. And essentially what we're going to be doing is the same thing we just saw earlier with the pancakes and eggs. We have our known quantity. That's going to be what we start with. So if we think about our dimensional analysis, we're starting with moles of aluminum. So that means moles of aluminum has to go on the bottom. And we can use the balanced chemical equation to then convert to any other substance. So if we wanted to figure out how much of the product could be produced from this 0.429 moles, we could figure that out. But we're interested in the iodine. So that'll just be the substance that goes on top. But with this dimensional analysis, you can see the reaction here. So aluminum and iodine are both going to be solids. But then with this reaction, produces so much heat that you actually vaporize the iodine. That's why you're seeing the purple vapor on the right-hand side there. But with this process, like I said, mole of aluminum on the bottom to cancel the mole of aluminum that we started with. Mole of iodine is what we're looking for. So that's the unit that goes on top. But just like with any other dimensional analysis, we need the numerator and the denominator to essentially be equal, so that we're essentially multiplying by 1. So with this reaction, if we go back for a second, we're saying for every 2 moles of aluminum, we need 3 moles of iodine. And that's why we plug in those values just as we have. So we've got 2 moles of aluminum on the bottom, cancels. We've got 3 moles of iodine on the top. And that's why that's the unit we wind up with here. But then also just remember, those coefficients in the balanced chemical equation are going to be exact numbers. So there's really an infinite amount of sig figs with the 3 and the 2 here. So that's why our final answer has 3 sig figs to match the initial 3 sig figs in the moles of aluminum. And then if we look at this sort of flowchart thing, we can see kind of the same idea. We're starting with moles of C3H8. So this is going to be propane. So if you've ever had a propane grill for barbecuing or whatever, C3H8 would be the fuel. And with it, we could combust that propane, turn it into carbon dioxide and water vapor. And if we knew how many moles of the propane we had to start, we could use that balanced chemical equation, just like we did for the aluminum and iodide here, to then convert between moles of propane of the reactant to moles of carbon dioxide that would then be produced. But earlier I mentioned that we may have one extra step at the beginning or the end or both. So what we can then do is use that moles of product, the moles of carbon dioxide in this case. We could use Avogadro's number to convert to the molecules of carbon dioxide. We've done that conversion before. Or more commonly, what we're going to see is that we're going to convert to grams. Because grams is something that we can actually measure. We can't measure moles of any substance on a balance, but we can get the grams fairly easily. And then we'll also see a very similar process where we're going to volume. So we're going to the liters. But With it, it's always going to be the same thing we've been doing. We're just going to have that mole to mole step kind of in the middle to help us link those two different substances together. All right, so for this one, what mass of sodium hydroxide, NaOH, would be required to produce 16 grams of the antacid milk of magnesia, magnesium hydroxide, and then we have the formula there. And we're given the balanced chemical equation. So it's balanced because we've got 2 sodiums on both sides, 2 chlorines on both sides, 1 magnesium, and 2 hydroxides. So the first thing we should always do is look at that equation, make sure it is balanced, to make sure we have the correct coefficients in front of those various substances. But in this case, we know how much of the milk of magnesia we want to produce. So what we need to figure out is how much of the reactant do we need. In this case, we're focused on the sodium hydroxide. We could also do the exact same thing for magnesium chloride. But with this, like I said, we can only go from moles to moles of another substance. So we can't go directly from 16 grams of milk of magnesia to the mass of sodium hydroxide. So with this process, what we're going to have is the mass. What we'll have to do with this one is the mass of substance A to moles of A. And then in this case, A is just the milk of magnesia because that's what we have information about. But it could be any substance in a chemical reaction. And then we'll be able to use the balance coefficient to go to moles of B. And then we can go to mass of substance B. So with this, again, doesn't matter which 2 substances we're interested in. We could know how much reactant we have. We want to figure out how much of the other reactant do we need. We could go from amount of reactant to the product, and we'll see that in a second. In this case, we're going in the opposite direction. So we can relate any 2 substances in a chemical equation, and the process itself is going to be the same. It's just kind of what are we looking for? What does that information represent? But if we think about it, mass to moles, and then moles to mass. So if we just split this in half and look at the first or the third step individually, we've converted from mass to moles before. We just use the molar mass. And then the same thing going in the opposite direction. We can still just use that molar mass. We'll just have to have it flipped in those 2 steps. And with it, since we've got substance A and substance B, we'll have a different molar mass in each of those. But we've done both of those steps before. And then the only one that's somewhat new that we just saw is this mole to mole step, just based on the coefficients in this reaction. So for the first one here, what we're going to do is take the 16 grams of magnesium hydroxide. And since we're starting with grams, we'll have to flip that molar mass. So we've got grams on the bottom, moles on top. That'll be our first step. Then we'll use the coefficients here. Since we have moles of magnesium at that point, we'll do 1 mole of magnesium hydroxide on the bottom, 2 moles of sodium hydroxide on top. And then, like I said earlier, we can't measure moles directly on anything. So we're going to convert to grams. That's something that we can easily measure in the lab. So then we're going to use the molar mass of sodium hydroxide just to convert from that many moles to whatever that mass is going to be. So if we look at the setup here, 16 grams of magnesium hydroxide. This is just the molar mass of magnesium hydroxide. So again, we've got grams on the bottom to cancel the unit we're starting with. We would be left with moles of that substance after the first step, but we want to keep going. So now we use the balance coefficient here. 1 mole of magnesium hydroxide on the bottom, 2 moles of sodium hydroxide on top. And that's just, again, coming from this balance reaction. So that's going to be why the balanced chemical equation is so important. And then the molar mass, just that final step again, but it's the molar mass of the new substance, so the substance that we're trying to find information about. So with the 40, that's just 1 sodium, 1 oxygen, 1 hydrogen added up. 58.3 is the same thing with 1 magnesium, 2 oxygens, 2 hydrogens there. But again, our sig figs going to match the sig figs in the initial value. So since we started with 16 with 2 sig figs, we're going to finish with 22, which has 2 sig figs as well. And with this process, it's always going to be very, very similar, just different substances. So we'll have a different amount initially. We'll have different molar masses for whatever those substances are. The balanced chemical equation may have different coefficients, but the process, sort of that general structure outline is always going to be the same. So again, if we just look at another one, in this case, it's octane, C8H18. What we have here is, in this case, trying to figure out the mass of oxygen. So this could be a combustion reaction. If we knew how much octane we had, how much of the oxygen would we then need to fully react with all of that octane? But it would be the same process. We could use the molar mass of octane to convert to moles of that substance. We could then use the balanced chemical equation. We could use those coefficients for octane and oxygen to relate them together. And then finally, we could use the molar mass of oxygen to actually convert that to grams, something that we can easily measure. And if we go back for a second, each of these can be known as mass to mass conversions, because we're starting with the mass of one substance, figuring out the equivalent mass of another. What we're also going to see is that we can do kind of the similar thing with volume, or even number of particles, so molecules or atoms. So if we take this sort of flowchart schematic and split it in half and just look at left or right, it's the same thing just for substance A or B. These are all conversions we've done before. So the molar mass to link mass and moles together. We can use molarity to relate volume and moles. We can use Avogadro's number to relate moles and number of particles. So all of these are things we've done before. Even density. So if we knew the mass, we could then get the volume of a pure substance. So we've done all of these conversions before. And then again, B is the same thing, just for a different substance. So depending on what we're looking for, we'll always have this mole to mole step in order to relate those two substances. But then if we're looking for the mass of a given reactant or product, that'll be where we use the molar mass. If we're looking for the volume of a solution needed, we would use the molarity to then relate moles and volume. Number of particles is less common, but we can still do that just using Avogadro's number. So we still just have to kind of think about what are we looking for, so we can think about how we set up that calculation. But most of the calculation is going to be stuff we've already seen. It's just going to be this mole to mole step that'll be kind of the new part. And again, we need that mole to mole step in order to relate those two substances, because the coefficients in those balanced chemical equations represent moles of those different substances. And then somewhat similar, we can use the reaction yields. So we can kind of do a calculation to determine how efficient a given reaction actually was. And with it, we're going to be using that stoichiometry setup. It's just with it, we're going to then be determining what's known as the theoretical yield. And we'll be comparing that to what we actually see. Actually, I'm getting a little bit ahead of myself, because with this one, we're going to first talk about limiting reactants. And essentially, when we're looking at the balanced chemical equation, we've got those coefficients. So we've got the exact number of moles of the reactants that we'll need, the exact number of moles of the products that'll be produced. But a lot of the times, we're not actually going to have each of those substances in the exact rate proportions or rate ratio. And with that, we're going to then have what's known as a limiting reactant or limiting reagent, and then a excess reactant. And with it, one of those, the limiting one, is essentially going to determine exactly how much of a reaction takes place. So if we think about a sandwich, very simple sandwich for a grilled cheese, we're going to say that in order to make a grilled cheese sandwich, we need 2 slices of bread and 1 slice of cheese. That's going to be by our definition what a sandwich is. So then if we think about the supplies that we may have 28 slices of bread and 11 slices of cheese. So we've got enough bread to make 14 sandwiches, but we've only got enough cheese to make 11. So we can only make 11 sandwiches, even though we've got enough of the one ingredient to make more. We just wouldn't have any cheese for those sandwiches. So in this example, the limiting reactor, the limiting reagent, would be the slices of cheese, because that's going to dictate how many sandwiches we can make. Whereas the other ingredient, or the other reactant, is just going to be known as the excess reactant, because we have that in excess. We have more than we need based on the other one. So in this case, if we were actually to make those sandwiches, we can make 11 sandwiches, and then we would still have 6 pieces of bread left over, just because we didn't have any cheese for those. We're going to see something similar in a lot of these chemical reactions. We can mix those things together, But we're usually going to still have a surplus, essentially, of one of those reactants at the end. So if you look here, again, one sandwich is 2 pieces of bread and a slice of cheese. So based on what we have there, we can only make 11 sandwiches because the cheese is the limiting reactant. So we're going to be left with 6 slices of bread afterwards. And if we think about a chemical reaction now, so we've got the balanced chemical equation for the reaction of hydrogen and chlorine to produce hydrogen chloride. And we can see 1 mole of hydrogen plus 1 mole of chlorine gives us 2 moles of hydrogen chloride. So if we had 3 moles of hydrogen and 2 moles of chlorine, that means we've got 3 moles, and we think about the mole to mole ratio. What we can do is figure out, based on both of those reactants, how much product could we possibly produce. And with the hydrogen, we've got 3 moles. We get 2 moles of HCl for every 1 mole of hydrogen. So we could make 6 moles of HCl based on that amount of hydrogen. But with the chlorine, since we only have 2 moles of that, we could only produce 4 moles of HCl. So in this case, the chlorine, since it can only be used to produce 4 moles of HCl, that's going to be our limiting reactant. That would be the one that would get completely used up if we were to mix these two together. And then we would still have 1 mole of hydrogen left over, just unreacted with. So with this, if we have information about 2 reactants, and we've got to figure out which of these is going to be the limiting reagent or limiting reactant, again, same term, what we can do is figure out for each of them how much of the product could we produce, and then whichever one produces less, that one's going to be our limiting reactant, just because that one's going to get used up first. So you can see here, if we had 6 molecules of hydrogen and 4 molecules of chlorine, we've got that excess amount of hydrogen. So that's why after this reaction takes place, we can react all of that chlorine to give us 8 molecules of HCl, but then we still have those 2 moles or 2 molecules of hydrogen gas left over, because that's going to be our excess reactant. And then this is what I was alluding to earlier, as kind of a measure of efficiency, is going to be what's known as the percent yield. And it's going to be based on the theoretical yield and the actual yield. So with the theoretical yield, this is always going to come from our stoichiometry. So if you think back to the aluminum lab we did, you started with a piece of aluminum can, we went through a series of reactions, and then you produced alum. And we were able to predict or calculate the theoretical yield by taking whatever mass of aluminum you had to start with, dividing by its molar mass, multiplying by the stoichiometric coefficients, which I believe were 1 to 1, and then multiplying by the molar mass of alum. And with that theoretical yield, like I said, it's always going to come from the stoichiometry. That's going to represent the best case scenario. So that's going to represent if 100% of the mass of your reactant gets converted into the mass of your product, how much could we wind up with? But in reality, the reaction yield is typically going to be lower than that. How much you actually wind up with it, or the actual yield, typically going to be less than that theoretical yield, for various reasons. One, there could be competing side reactions. So what that means is, as we have a reaction take place, there's going to be the reaction that we're focused on, the reaction that we want to occur, but we may have other reactions going on as well. So if you think about it kind of as a roadmap, we might want to just drive straight down the road, but the reaction may kind of branch off to the side. So we may have other things occurring that are going to decrease the yield of the product that we actually want. It may just be kind of an incomplete reaction, in the sense that you may not have fully mixed everything together. You may not have heated everything up properly. I guess technically, if you had too little of another reactant, then you just not fully react something. That'd be more of a issue with the setup of like your math, rather than a mistake like these other ones, or an issue like these other ones. It could even just be user error. So you could have spilled something, and that kind of goes along with not mixing something well enough or heating it properly or whatever it may be. And then even difficulty recovery of the product. So depending on the state of matter, it may be, and if you have to transfer something multiple times, you may not be able to fully get all of that sample out each step. So you may be losing a little bit of it that way. Certain reactions just don't work extremely well to begin with. So like that Illum lab, theoretically, you could get 100% of the theoretical yield. That's the case with every reaction, but with the Illum lab, typically the yields are much lower. And that's just a case with that particular experiment, but that happens with other ones as well. But once we have the actual yield, once we calculated the theoretical yield, we can use those to quantitatively kind of assess the efficiency of that reaction just by using the percent yield. And simply what that's going to be is the amount that you actually wound up with. So we could just finish our reaction, take the mass of our sample, and then divide it by the theoretical yield, which again is always going to be from the stoichiometry. So that's the best case scenario. That's if law of conservation of mass, if we have everything turn into that product, it'll be perfect. But again, that's never really going to happen. There'll always be some minor issues at least with whatever reaction you're focused on. But with this, just note that the actual yield, that's going to be a mass. So that'll be something in grams or kilograms. The theoretical yield, we need it in the exact same unit. So just with like dimensional analysis, if we've got a unit on top and then have that same unit on the bottom of a later step, those units cancel. It's going to be the same thing here. So we'll either have like grams over grams, kilograms over kilograms. I guess you could have moles over moles if that's what you converted your units to. Not that you could get that from the balance directly though. But whatever those units are, they're going to be the same on the top and the bottom. And that's why with this percent yield, the unit itself is only just going to be that percent sign. So we'll never have like percent grams or kilograms percent or anything like that. It'll always just be like 73% yield or whatever the yield is going to be. So to see an example here, we've got a reaction of 1.274 grams of copper, should be copper 2 sulfate, with excess zinc. So it's telling us we've got excess zinc just to ensure that all of that copper sulfate could react. And if we only had like 0.01 grams of copper, or 1.01 grams of zinc rather, that's certainly not going to be enough to react all of the copper 2 sulfate. But at the end of the reaction, we actually obtain 0.392 grams of copper. We want to figure out what the percent yield is. So this is going to be where we have to use that percent yield equation. But before that, we've got to think about what the theoretical yield is. So we've actually got to figure out if we started with 1.274 grams of this reactant, how much of the product could we wind up with? So we're going to need to use the molar mass of both of these. The coefficients are just 1 to 1. So that second step is just going to be 1 over 1. So we'll have the same number of moles of copper sulfate as we have copper in terms of the theoretical yield. And then we can just use the molar mass to convert to grams to compare it to the actual yield we have here. So for the theoretical yield, we start with the amount that we actually have, 1.274 grams. We can then use the molar mass. So if we added up 1 copper, 1 sulfur, 4 oxygens, we're going to get a little bit under 160. So we can do this first step to convert to moles of copper sulfate. And then if we go back for a second, coefficients of 1 for every substance here. So for every 1 mole of copper sulfate we react, we're going to produce 1 mole of copper. But we want the amount of copper in grams so we can compare it to that actual yield. So then we just use the molar mass of just copper now, 63.55, in order to convert that to grams. So this 0.5072 grams of copper is the theoretical yield if we started with 1.274 grams of copper 2 sulfate. So again, that's the best case scenario. That's if this reaction works 100% perfectly. But in reality, we only recovered 0.392 grams of copper. So we do the actual over the theoretical, 0.392 over 0.0572, or 0.5072, excuse me, and then multiply by 100 to make it a percentage, and get 77.3%. And then again, when I mentioned the units cancel earlier, now we've got grams of copper over grams of copper, that's all going to cancel. So we're just focused on the values now. And with this, we're not really going to go into it here, but there's a similar kind of idea where rather than percent yield, where it's looking at atom economy, and that's also sort of a measure of how efficient a reaction it is, where percent yield, you're looking at how much could you have wound up for that product? What did you get? Kind of comparing those two. With the atom economy, what it's looking at is of the atoms that you use in your reactants, how many of them wind up in the product of interest. So a lot of the times a reaction may have multiple products, but we're only going to be interested in one. We're going through that reaction to produce a certain substance, but we might just have some byproducts, some waste produced along with it. So with the atom economy, if we could have 100% of an atom economy, what that means is every atom we react winds up in the product that we're interested in. And with it, that's going to be something that is going to be important industrially, along with the percent yield. Because if you think about it, in both cases, if we've got a reaction that's got a really low percent yield, and industrially they're producing huge quantities of that substance, if it's got a low percent yield, that means they're wasting a whole bunch of substances. They're going to want to try to find a different way to produce that that's more efficient, doesn't have to use as much starting material. And then the same thing with atom economy. If we can go through this reaction and have everything then make it into the product that we're trying to produce, that's going to reduce the amount of waste overall. So that's going to be good environmentally, just because there's less to dispose of, but it's also going to be cheaper for the company because then they don't have to pay to dispose of that waste. So if you think about in the lab, with most of the substances, we've got to make sure we put them in the correct waste containers rather than just pouring them down the drain. That's going to be the same thing with pharmaceutical or chemical industrial companies, whatever they may be. They're, of course, also thinking about how to maximize profits. So if they can reduce waste, make that more efficient, they can save money, make more money. But also environmentally, it's going to be a benefit as well. I would say they're probably more concerned about the money though in general, which for pharmaceutical companies, certainly not what you'd want, but what are you going to do? That's America. And then with the final piece here, quantitative chemical analysis. So with analytical chemistry, there's kind of two main questions. What is something? So determining the identity of that substance. And that would be a qualitative analysis, determining what it is. Quantitative now is looking at how much of it is there, basically, or figuring out what portions of something is X, Y, and Z. And there's going to be different ways we can kind of do that depending on the substance, depending on the type of sample, whatever it may be. And we'll look at a few of them here. The first one being titration. So that's something that we should already be familiar with because we've had a lab where we've standardized sodium hydroxide, determined the concentration of that, and then we'll also have another one coming up where we use that same sodium hydroxide to analyze antacids. And then gravimetric analysis, we'll see later on as well. But with the titration, we didn't put these terms to it when we did that first titration experiment. But if you think about it, we had two solutions. So in each case, one of them was the sodium hydroxide, and then one of them was either vinegar or KHP, potassium hydrogen phthalate. With it, we also had one in a burette, we had one in a flask. The burette versus flask part doesn't really matter at all. But with the titrant, that's going to be the one that we know the concentration of. So when we were doing that experiment at first, we knew the concentration of the KHP, or at least we could calculate it. We were only interested in moles at that point, but we knew how much of it there was. Whereas with the sodium hydroxide, we knew the approximate concentration because we knew it started at roughly 6, and then we knew how much we diluted it. But that's the one that we were actually determining the exact concentration of. So the analyte for that first part of the experiment would be the sodium hydroxide. But then for the second piece, we use that sodium hydroxide after we determine the concentration of it to then analyze the concentration of vinegar. So in the second part of that experiment, now the sodium hydroxide was the titrant, and the vinegar, at least the acetic acid in the vinegar, was the analyte. And with that experiment and with a lot of these titrations, it's not always the case, but a lot of the times indicators are going to be added to the analyte, or just added to the flask, because again, it doesn't matter. Typically, the analyte will go in the flask, but you can have them in either place, whether it's the burette or the flask underneath. But typically we add an indicator so that we can actually see this reaction take place, because if we think about just an acid-base reaction, for instance, it's going to be colorless, it's not going to produce gas, or at least depending on the acid-base. But it's going to be colorless, we're not going to really see anything occurring. Both of those solutions typically look like water, and when we combine them, it's going to continue to look like water. So we use the indicator to let us know when we've reached that endpoint. And with the endpoint, that's just referring to when that indicator changes color. So the endpoint is just when we have that indicator change. But just know that's different than the equivalence point. With the equivalence point, we're going to have an equal amount of acid and base. And generally, they're very, very close, but they are going to be different. So with the equivalence point, again, equal amounts of acid and base, if we're thinking about an acid-base titration. The endpoint, though, is going to be where that pH change, or where the indicator changes. So with phenolphthalein, that pink indicator that we used, or the indicator that at least turned pink, that changes, I believe, at around 8 or 9 pH, a pH of 8 or 9. Whereas the equivalence point, if we had a strong acid and strong base, the equivalence point would be at pH of 7, perfectly neutral. So the equivalence and the endpoints are off slightly. But because, and if you think about how hard it was to get that very, very light pink color during the titration, if you use just a fraction of a 1 extra drop, you'd go to a much darker pink, kind of purpley color. And that's going to be because once we approach that equivalence point, now we've got an equal amount of acid or base. So as we just add a little bit extra of one or the other, we're going to see that the pH changed drastically. So effectively, the equivalence point and the endpoint, as long as we choose the proper indicator, are going to be effectively the same. And then with the burettes, remember I mentioned to make sure to never pour above your eyes, just so in case you spill. So I'd always recommend, if you're taller than the burette, you don't really need to worry about it. But if not, you can always take the burette out of the stand and just pour it that way. And then with these burettes, at least the ones we'll be using, and the one you can see in the image here, goes up by 1/10 each time. Each of those lines represents 0.1 milliliter. So with them, we can always estimate 1 digit further. So we can always estimate to the nearest hundredths. And then with these, just remember, they kind of count backwards. So in this case, the meniscus is above 1, but it's in between 0 and 1. So I would say this is probably 0.38, maybe 0.36, 0.3 something, because now it's in between the 0.3 and the 0.4. Looks to me a little bit closer to the 0.4, but we can estimate that hundredths place. All right, so if we look at this one, we're going to get an opportunity to see that stoichiometry again, but in this case, we're going to be looking at solutions. So it's going to be a very similar idea. It's just instead of using the molar mass, now we're going to use the molarity to relate the moles of each other, or relate moles and volume. So if we look at the reaction, acid-base reaction, so we produce salt water. And since this is sodium hydroxide and hydrochloric acid, that salt is just going to be table salt, sodium chloride. But it tells us the endpoint of a titration of a 50 milliliter sample of aqueous hydrochloric acid was reached by addition of 35.23 milliliters of 0.250 molar sodium hydroxide. What is the molarity of the HCl? So with this one, we've got several pieces of information. So we've got to think about, what do we want to start our dimensional analysis with? We'll ultimately see there is a different way we could kind of solve this, because it's acid-base, but we're going to focus on the stoichiometry for now, because this process will work for any reaction. But But with it, we've got information about HCl, we've got information about sodium hydroxide. So we want to think about what we're trying to determine, the molarity of HCl. So since we're trying to learn information about the hydrochloric acid in this case, what we're going to want to do is start with the amount of sodium hydroxide. And if we think about what we're looking for here, molarity is going to be moles over liters. We've got the volume of hydrochloric acid, we've got it in milliliters, but we've got that volume, so we can convert to liters. We can just move that decimal to the left 3. We'll see that the volume is going to be 0.05000 liters. But what we can do is use the volume, using the molarity of sodium hydroxide, to figure out how many moles that is, and we can then use the balanced chemical equation to figure out how many moles of HCl would then be present. So what we're going to do is start with the 35.23 milliliters. And remember, this capital M really represents moles per liter. So we're going to be able to use that to relate volume in moles. But since this is moles per liter, we need to convert 35.23 milliliters to liters first. So we're just going to divide by 1,000, get it into liters. And then since we had a 0.250 molar solution, that means for every 1 liter of solution, we're going to have 0.250 moles of sodium hydroxide. And then based on the balanced chemical reaction, for every 1 mole of sodium hydroxide, we're going to have 1 mole of HCl. So that'll just be our final step here. And with this particular question, since we're looking for the molarity of HCl, we've got to go 1 step further. So we've got to then take this moles, this number of moles, and divide by the liters of solution. So again, since we had milliliters to start, we've got to make that conversion. So we're going to see we'll have a 0.176 molar solution in that case. If we go back here, we can see again, very similar to what we did with the mass-to-mass conversion. It's just in this case, we use the molarity rather than the molar mass to link the volume with the number of moles. Let's stop here. Oops. So I'm going to stop here. Then we'll save the gravimetric analysis for the final piece of this video.